We're going to go through several series of things in these circuits, how they work, how electricity flows. Electricity has a path. Does anybody know what that path is?
Least resistance.
The path of least resistance. So if you have electricity going to a light fixture, it's going to go the path of least resistance, okay? So here we have an in series circuit, a parallel circuit.
It can't be.
And in series and parallel circuit are a combination circuit, okay? So here's your source. It always goes from plus to minus, right? So even with your electrical outlet, you have your power, and then your power always returns back to what? Your neutral every time. It has to have a path of flow. If it doesn't have a path of flow, you've got a problem. That's where continuity comes in. You can actually put it on your wire here, put it on your wire there, and see if you don't have any breaks in there. It'll give you a signal. But that's all continuity is good for. It's testing one wire from one end to the other to see if there's not a break in the wire. The hardest ones to find is where it has a break in the wire that you can't find until you actually bump the wire. So I've had my alligator clips on one end of the wire knowing that I've got a problem there somewhere, and I accidentally bumped the wire, and it gave me a signal saying I had an open load. Then I went and found it. About halfway through that wire, I can move it back and forth, and I can get connection and not get connection. That happens also with heat and cold. When it's cold, it's connected. But when that wire heats up from the electricity or the power going through it, it may open up and then not work. So those are the ones that are hard to find, but that's something you need to know about so that you can look for them. Doesn't always mean that there's not a problem in that wire. So I've seen that many a times. Electrician for 16 years, had a wire that actually broke right in the middle somewhere, especially on the neutral side, and get a voltage surge through something and can't figure out why, because I have a wire that's still got its coating on it that's broke inside. Okay? So in series, both of those little diodes, or LEDs, light emitting diodes, will come on. In parallel, they'll both come on unless there's a break. Parallel and series, they'll all come on unless there's a break. So we're going to simplify the troubleshooting process, tackle appliance diagrams with confidence. After completing the lesson plan, you'll be able to describe the three main types of circuits, identify similarities and differences between the types of circuits, and explain the differences between an open and a short. Circuit series. Are these all in series? They're all in series, right? These are all lights. So you have your power coming in, your power coming back, and then you'll always have a ground. On appliances, are we required to have a ground for them to work correctly?
Yes.
Absolutely. When it comes to computer boards, they do require a ground to work correctly. Okay? Any surge or anything goes directly to ground, that protects the circuit board. So make sure that they are on a designated circuit and that they have a proper ground. If you go in, you plug in your little tester that does not show they have a ground on there, they need to have that fixed. Anybody know the quickest way to fix ground on a refrigerator that goes to the outside wall? Drill a hole to the outside wall. Huh? No, don't go to the plumbing. We don't ever want electricity to surge back into water. Because what does water do? It conducts.
I know on my water meter, they ran the ground right to my house.
They don't need to do that, not ever. Quickest way to do it is drill a hole to the outside, stick a number 4 copper wire in, stick that number 4 copper wire 6 foot into the ground, and you have a proper ground. 6 feet, okay? Most of the ground rods that you can drive in are 8 feet to 15 feet or 16 feet deep. Okay, I just redid the electric panel in my house. I had to drive a ground rod in and for my area, it had to go 12 feet. Okay? So I had to rent one of those electric hydraulic pounders, get it up on top of that baby, and drive it down into the ground till I had it 2 inches out right by the base of my house. So I went 16 feet, so I had extra. And then attached the ground to my electric panel, because guess where mine was? It went up over to the water pipe going to the water heater. It's not a proper ground. It won't even show an actual ground in the home. Okay? It's going back to water. Water conducts electricity. It causes electrolysis within the water heater. If it ever does go back that way, it causes more problems. So make sure it has a proper ground.
Sometimes they break the ground falling off there.
Sometimes they do, or they put one of those adapters on there. Your appliance will not work correctly, it will cause problems. Okay, so there's your little Christmas light series. One bulb goes out, everything behind it goes out, doesn't it? So if you have lights on to one point and then they're out, that's the way it works. Oh, if one goes out, the whole string is out, right? Okay? So here's a circuit, a series circuit with a switch in it. Just like a flashlight, you push the button on the switch, or if I push the button on this little LED, I get my light, right? It actually connects the power through it, so that's what your switch is for. That is also called an open. So if you're tested and you don't have anything open, you might look for a switch. You go in somebody's home and guess what? Their dishwasher's not working. Turn on the switch to the garbage disposal when the dishwasher works. Oh, they've got it wired in wrong. They forgot to pull out the little tab and put the extra hot down to the bottom so that they had a separated circuit. Okay? What type of circuits are these, guys? Comes in, just flows all the way around, right? Even if it does this, still flowing all the same path, right? So these are still all in series. Different types of looks for different series circuits. Parallel circuits. Again, they're all going to be in parallel. They're all going to have their own line source and their own neutral source, okay? So your power is going to come in, go through your load, come back out, of course, to your neutral side, and of course it has to be grounded. Voltage equals IR. What does IR stand for?
Current and resistance.
Huh?
Current and resistance.
I can't understand you.
Current and resistance.
Current and resistance. Okay, you're right. So voltage equals currents and resistance. Here's a couple of different types of parallel series, or parallel loads. This is a parallel load. What's wrong with this one though? It's got an open down here at E, doesn't it? So is this light going to light up? No. What side is that open on? It's on the neutral side, or the return side of the power, right? If it was over here, where would it be? Be on the positive side or the load side of it, right? Okay. Where's our open on this one? F. So is that open on the load side or the neutral side? It's going to be on the load side, right?
Yeah.
So this is going to be your power side or your load side. This is your actual load, and then you have your return. Okay. So is D going to light up?
Yeah.
Yeah, D will light up because it lights off right here, branches off, right? What about here? Is anything on the light up?
No.
Okay. How about over there? Is anything on the light up?
Yeah.
C and E will light up, okay? And what What side is this on?
Return side.
It's on the neutral side of the return side of your load, right? Or return side of your power. Okay? Combinations, you got series and parallel. Most of your circuit boards have series and parallel in them. You need to be aware of what you're testing in, okay? So if it has to go through several other things to get to what you're powering on, what's it gonna be?
Combination.
In series. If it has to go through something else in series like it does here, oops, go back a couple, like it does here, and then go over here for the parallel. We have a break here, is it going to work?
Break here?
Right here.
Oh, that ain't gonna work.
What if we have a break over here?
Yeah.
Is any of it gonna work?
Nope.
Nope.
Absolutely nothing's gonna work, but what if we have a break right here?
Yes. Mine will work.
So these will all work,
Center and bottom, yeah.
but that one line up there won't, okay? So you gotta know how your path flows and how your circuitry is working in your system. Okay? Again, here's some more parallel, different setups on those. This one over here has a switch, but what do we have here? So is anything on that side gonna light up? Okay, so that's an open load. What if I had a wire that accidentally come from right there to right there? Laying across that, what is that?
Short?
That's gonna be a short to ground, right? Is anything gonna work in that circuit?
No.
Okay? Why use combination circuits? Different parts of the appliances may require different voltages or currents. How many different types of voltages and currents do we have in our appliances?
Several.
Several, like, we have AC coming in, but it may invert or convert to DC, right? What is your normal operating voltage in an appliance? Does anybody know? No?
Oh, inside it?
What is your operating control voltage?
12 VDC.
5 volts is usually your operating, and 12 volts is usually your power source,
Wow.
okay? So 5 volts is going to tell it what to do, and 12 volts is what's going to actually run it. Just like the fans in these refrigerators back here. If they're a DC fan, they're running off a 12-volt circuit. They only may run 7 to 8 volts. That's all they need to run that fan. But that's coming off of a 12-volt DC circuit. It usually has a capacitor right before it to drop that voltage down to its operating voltage. It's what it's going to take to make it operate. But the signal that comes to it is coming from the 5-volt side. When that compressor starts, guess what? There's a little relay up on that board that says, I'm ready to cool. It's going to send a signal down there to the other board. It's going to send the voltage out, okay? So you see that other little 5-pin connector on the right-hand side of your inverter board? That's its control voltage. It's telling it what to do. I'm ready to cool, turn my compressor on. And then that inverter board is going to jump that power up from 120 to anywhere from 160 to 220 volts and turn that compressor on, okay? And if it is a VCC, a variable control compressor, it may step it up in stages and step it down in stages as it needs. If it needs to go to full cool, it's going to go to full cool. You may have 210 volts on there initially. Then it's going to drop down to medium when it says, hey, I'm getting close to where I need to be. I'm going to drop it down, save a little power. It's going to drop your frequency down. It's going to drop your voltage down. You're going to look and see anything from 160 to 190. And then you're going to look at it again. It says, okay, I'm right at the point I need, but I need to just kind of tip it off just a little bit. I'm going to drop down to low. And it's going to run anywhere from 130 to 160. It's going to drop the frequency down again. They use frequency to control those variances, okay? It's also known as a variable frequency drive, but they call the compressor a VCC, the variable control compressor, okay? But frequency is what they're using to up up and down that to control the speed of that compressor and how much cooling it's going to do. Okay, does everybody understand that? Yeah, Daniel?
Okay, so you said 5 volts is normal operating voltage, and 12 volts is what?
Running source.
12 volts is your running source.
Normal running, so.
Under load in the power supply.
Yep, under load on power supply. Okay? So that's just a few things about how these appliances work. Most everything that you have back there, your washers, dryers, 5 volts of non-control voltage, 12 volts on some circuits, 120 on the others. Okay?
So, I have a question.
Yeah.
With the way that centrifugal switch works, it would kind of be the same thing to apply out of the swing when you're receiving the load and power transfer going from 5 volts to 12. You're
Right.
operating, right? So when that centrifugal switch kicks in, now you're gonna receive more power versus the 5 or 12 volts. You're gonna get 12 volts at that point.
Okay, no, you're still gonna have the 120 volts, but when that centrifugal switch kicks in, it's going to allow that 120 volts to go from there further down the line to its actual,
Yeah, okay.
okay, which goes to where, do you remember? It goes to your heater, right?
Yeah, it goes to the meter.
Okay, but then that centrifugal switch is gonna do a second thing. It's got a control voltage side of it too. It's gonna send that signal up to the relay and tell L2 on the relay to send the other 120 volts down there, so you have 240 volts across that heater to cause it to come on and heat.
Okay.
Okay, does that make better sense?
Model.
Okay, if that makes better sense, that's how that works.
Yeah, no, that makes sense.
Yeah,
Yeah.
but that signal has to go back up to that board, so once that motor reaches speed, and that centrifugal switch pops in,
It's sending
it's
back-
sending another signal back up to the control side of the voltage to tell L2 to go ahead and go to the board, go from the board to the heater. Okay? All right, so here again, we've got our switch. If that switch is open, it's gonna be an open load, but then we have an open here. Is anything downstream of that gonna work? What about over there? Is anything on that circuit gonna work?
Nope.
That's a broken what right there? That's a broken neutral. Okay. All right, so we got 3 lights on and 1 off. What do we have down here?
Broken neutral.
Broken neutral. Okay. So don't assume that nothing's gonna be on the neutral side, because if you go back there and work on those dryers, what's the door switch on? Door switch is on the neutral side, right? There's actually several components in those, in your washers too, that are on your neutral side. How do you test those? Can you test the power through it? Well, there's no power through it, it's coming back off the neutral side, right? So they're breaking the neutral. That's where you ohm that out. Continuity to that switch, continuity past the switch, push the switch and see if you got ohms. Ohms is your best friend when it comes to using a meter. Okay? So what type of circuit is this? Series? Okay? This? Parallel? This? Combination? This? Okay, so let's practice. We're not gonna do the snap circuits this morning. So let's look at some short circuits, okay? You ever seen a short circuit do that?
Yeah.
I've walked in many homes and guess what? Looked like there was a fire on the dryer plug. The neutral burned up in the wall, overheated the plug, too much voltage coming to it. That's a real thing. Okay? But the most common place that you're going to see that, where it has a little smoke out like that, is on the back of your ranges or on your dryer element where the wires have actually burned into going up to it. Okay? So you see that little connector on the end has burned up. That wire's broke completely off. What is that going to be due to?
Short circuit.
Short circuit, over amperage, the burnout element could cause that wire to burn just like that on the back of that range. Are you just going to test it on it out and see if it's okay? You're going to get a new wire harness, you're going to get a new element, you're going to change it all out, right?
Yeah.
Okay? Is that going to affect the control board if that happens?
It potentially,
It potentially could, yes.
just because it burnt there doesn't mean that the power didn't stop there. It could-
If it surged back to the board, it could actually fry the board at the same time. By the way, that's why they started putting TCOs on the back of the ranges, is to keep that from burning the board up. It'll surge back, trip that TCO, and solve a lot of problems. Make it a lot cheaper and easier to fix. So do we go in and just replace a TCO or a fuse?
No.
There had to be a reason for it to break, right? For it to pop? Check and find out why. There has to be a reason for it, don't just assume. Okay? Wire short out the load. So if you see something that, and what is the most common short that you'll find in an appliance?
Fuse, being
Huh?
blown, like fuse being blown.
A fuse can blow, but that's not really going to be to it might be to a short, but where's the short at? So if you see wires that are actually rubbing against the cabinet or something that's rubbing against the vibration of the drum or something, and it wears a hole in it, that's probably gonna be your short. Okay? Another thing that you can find shorts on is, when they went to install the cord on the dishwasher, and the electrician dipped the cord, and he didn't see it, he throws it up under there, and you get a little water under there, and it shorts out. And he nicks in those cords and everything, do you just put electric tape around it, hope it works?
No, you know.
No, have the customer replace it, don't do that.
There's a model of dishwashers where the drain pump leaks, they cause corrosion, it separates, you ever see that one?
Yep, it'll separate the wires, and separate the connectors on it.
Yep.
Yep. And there was a problem on washing machines, top-load washing machines a while back, that Samsung had to send a new harness out. Where the red wire going to the, motor assembly, the drive motor under there, to work the clutch, was really tight. And every time it went into vibration, it started rubbing and causing a problem. And it would actually break and cause a direct short and short out that motor. So you can find that stuff all the time. So just be aware those are out there. Okay? We have another short here, right? C to D is the short, right? Is anything back there gonna work?
No.
No?
Lights.
Electricity's gonna go what? The shortest path, right?
Yeah.
What if that shortest path is from here to here in your hands? Where's that going? Right across your heart, right? Literally right across your heart. Is that gonna be a good thing? Okay. You will find that when you get in your toolkits, that you're going to have a little grounding strap when you're working on these boards and stuff. Put it around your wrist and clip it down there where your ground wire is. And if you do shock yourself, it's gonna go straight to ground right there. Not gonna go across your heart, you'll be a lot better off. Okay? Especially when it comes to high voltage capacitors. And also be aware that they are putting capacitors on refrigerators now. Some of them on the boards, some of them at the compressor. So refrigerators do have capacitors on them, and some of them do, some of the bigger ones do have a HOAMP in that capacitor, so be careful. Don't assume the microwave only has the dangerous one, because they could be in these other appliances. All right, so what do we have here? Do we have a short anywhere?
Yeah.
We do, right?
That switch is closed, so.
That switch is closed, we're not going to have G working, right?
Right.
So what we're doing is we're bypassing one side of it to go to the other. What else can mimic that in an appliance, do you know?
Switch, a door switch.
Door switch can be stuck. You're missing your, little selector knobs on your washers and dryers. They actually bypass all the other functions they don't need to do the function you want, right? It's designed to be that way, so some of these may have it designed in there to go around that particular circuitry. So don't assume that it's just a direct short or direct short to ground. It may be designed that way for an operating function. okay? They don't really need this light right now. So guess what? The light's not on. What happens in a washer or dryer when you open the door? The light comes on, but when you close it, the light goes off. That is a design feature. So don't think there's a problem. There's not. It's designed in there. So if you see a switch in there like that, it's a design feature. Okay? This is a direct short. Is anything gonna work? Nope.
Nope.
Nothing's gonna work on that one either, huh? Okay? Okay, so you can test with the ohms and get open and close. What does OL stand for on your meter?
Open load.
Open load. Okay, so do we have an open load or a closed load here? Okay, so this is closed, so the power's gonna go through, right? What about here? Do we have an open load anywhere?
Yes.
And X.
Oh, an X in the light bulb, huh? That little filament's burned out. Here?
No.
Everything look good on this one? It's going to work?
W ain't gonna work, yeah, switch is gonna.
Yeah, it's right. W's not gonna work if that switch is closed. It's gonna bypass it. Got a little tricky one there, wasn't it?
Well,
What about here?
well,
Okay.
Alrighty then.
yeah.
All right.
What is
What
this?
brought us in the morning?
What is this? What is this schematic of?
That would be a microwave.
Oven.
Oven, yep.
So here's your control board. Here's your control board, and here's all your surface and burner switches. Okay?
Is that open right there with those two double arrows on, at the bottom left of those flicking?
No, that's just showing you the path of the power.
Okay.
Each of those infinite switches have to be closed before this is going to work. Okay? Now, I told some of you back there working on ranges, what's the difference between a potentiometer and an infinite switch? A potentiometer and an infinite switch.
Why you use bad words, man?
They're good words, potentiometer. Okay, so again, a potentiometer is like your switch on a fan, where you go from one speed to second speed to high speed. It only has 3 designations. It just goes to different power levels at those designations. But an infinite switch continues that power and raises the power as you move it up, okay? So if you're moving an infinite switch, you can go actually between 1 and 2 on your range and actually give it that little warmer temperature that you want to maintain whatever you're cooking on the stove.
So the only difference is one just auto determines what you're getting regardless of the other one you can fine tune, right?
But the other one you can fine tune, so it's pretty much the difference between them. But that's why they call them infinite switches, is because they don't have certain selections.
Same thing on the.
Now, if they're on the old ranges, they have the little round coils. They'll go click, 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 1, 2, 3, 4, 5. It's literally just giving you what you have right there, and you can't fine tune it. What were you gonna say?
Oh, like on a fan or a light as well, some people front room have.
Yeah, yeah, so now, if you push a light on that has a dimmer switch,
Right.
you can actually tweak that, how you want that light in that room, right? So is that gonna be an infinite switch or potentiometer? It's gonna be more of an infinite switch. A lot of people don't even know they have infinite switches in their homes. But there are some of them out there that you can push on. You go click 1, click 2, click 3, click 4, click 5, has 5 different levels of lighting. That's a potentiometer. Okay? Potentiometer has settings and infinite switch does not. That's the difference between the two. So this is, of course, like we said, an oven or a range. It's going to be a range because we got the burner, surface burners right here, right? Okay, here's your spark module. What type of appliance is this one?
Washing machine.
Yeah. What? I couldn't be a dishwasher, because there's a drain on it. Wash machine, no, it still could be a dishwasher.
It's a machine.
Yeah, there's a drain pump, yeah, the drain is expensive.
That's a dishwasher.
So you got a drive motor here.
That's a dishwasher.
What do you have up here?
flow meter, yeah, it's a dishwasher.
You see at the bottom?
Flow meter.
Yep. So here's your interface filter, okay? Dispenser switch, this is gonna be a dishwasher. Temperature sensor, door lock switch assembly, main switch. Okay? You gotta be able to recognize these sometimes by their schematics since it doesn't actually tell you what they're going to be. Okay, so let's look back at a few things, 3 main circuit types. Okay? What questions do you have? None right now, we'll go back to those later.